Look closely at a smartphone camera, a microscope, or even your own eye. You'll find a curved, transparent material capturing and guiding light. These are lenses, invisible tools that allow us to process the visual world. Light travels in a straight line. Fired through perfectly flat glass, it passes straight through unaltered. But curve that glass and the light slows down. Hitting a curved surface causes it to bend. This is refraction, light changing speed and direction entering a new medium. By engineering the exact shape of that curve, we control the speed of the light, deliberately bending it to send those rays exactly where we want them to go. That control relies on two distinct shapes. The first is the convex lens. You can identify it easily because it is visibly thicker in the middle and thinner at the edges. Because of that bulging center, convex lenses act as light gatherers. When parallel rays of light hit the glass, the curve forces them to bend inward, squeezing them tightly together on the other side. The second shape is the concave lens. This piece of glass is the exact structural opposite. It is thinner in the middle and thicker at its outer edges. That inward curve makes concave lenses act as light spreaders. As parallel rays strike the surface, the shape forces the light to bend sharply outward, pushing the rays away from the center line. A lens acts as a gatherer or a spreader, based entirely on whether its center is thick or thin. That simple physical difference dictates how every optical device operates. Let's look closely at the gatherer. When a convex lens squeezes incoming parallel light rays together, they all intersect at one precise mathematical location. We call this the focal point, the exact distance where converging rays meet. Place an object far away, and light rays pass through the lens and cross over. This projects a smaller, upside-down image on the opposite side. Because the light rays physically meet to create this projection, physicists classify it as a real image. A real image is an optical reproduction formed by the actual convergence of light rays that can be projected onto a surface. Here, the real image is inverted and diminished. But slide that object past the focal point, close to the glass. The exiting rays spread apart. Trace them backward, and they appear to intersect behind the object, forming a massive, upright projection. Since the actual light rays don't physically meet there, this is called a virtual image. A virtual image is an optical illusion formed by diverging rays that appear to originate from a point behind the lens. It is erect, meaning completely upright, and highly magnified. This is the exact mechanics of a common magnifying glass. A convex lens changes its behavior completely based on the object's location. Depending on where you place an object relative to the focal point, the lens will shrink, flip, or magnify the image. The concave lens behaves very differently. Its rays spread outward, so we have to track those diverging lines backward to find the focal point. In this case, that point is a virtual location on the incoming side of the glass. Because the physical light rays are constantly moving away from each other after they pass through, they never physically intersect. It doesn't matter if you place an object an inch away or a mile away from a concave lens. It will consistently produce a smaller, upright virtual image. A convex lens is distance-dependent. A concave lens is entirely rigid. It follows one strict rule, giving you a diminished, upright illusion every single time. Because they look like structural opposites, people often assume their optical outputs are exact opposites too. The facts show a different relationship. A convex lens can enlarge an image, or it can shrink it. A concave lens only shrinks it. You can prove this with a blank screen. If you aim a convex lens at a light source, it will converge the rays to paint a sharp, tangible image right onto the surface. Swap in a concave lens, and the light simply scatters, leaving the screen completely blank. Convex lenses create real projections you can catch on a wall. Concave lenses create virtual illusions that only exist when you look directly through the glass. We use these specific properties to build our world. Inside a digital camera, a convex lens uses its gathering power to capture light and project a real, inverted image perfectly onto the flat digital sensor. If a person is far-sighted, their eye fails to bend light sharply enough. We place a convex lens in their spectacles to gather and converge the light early, before it even hits the eye. If a person is nearsighted, their eye bends light too sharply. We give them spectacles with concave lenses to spread the light out slightly, delaying the focus so it lands perfectly on the retina. For exploring deep space, we stack them. Telescopes use a large objective lens to gather faint starlight and a second eyepiece lens to magnify that gathered light for the observer. From correcting our biological vision to observing galaxies billions of light years away, modern optical engineering relies entirely on stacking light gatherers and light spreaders. Every single time modern technology helps you to clearly see, you are relying entirely on the predictable geometry of bent light. You can test this geometry yourself. Find a pair of reading glasses or even a shiny soup spoon. Hold it close to your face and slowly move it away. Keep your eyes on your own reflection. Watch closely for the exact fraction of a second when your face flips from right side up to upside down. The moment you see that flip, you have found the focal point, hiding in plain sight.